Hello, here we will look at the important tool in the story of orthogonal linear algebra where we care about distances. This tool is orthogonal projection. And the setup is as follows. So we have a subspace in a vector space, and we look at a vector, the other way around. I want my ambient space be V and subspace be U, otherwise I will be confused. And we have a vector somewhere in the space outside of the subspace. So to illustrate the situation, let's imagine a subspace like this plane in a tree space, and then we have a vector sticking out perhaps. What we will be after is the decomposition of a special shape of the vector as a sum of two. The first is orthogonal to the subspace, perpendicular to it, and the second, called the projection, is a vector inside. So schematically we will have this shadow as if the midday shadow is as if we're looking at the vertical shadow of our vector. So this component will be the orthogonal summoned in the decomposition of vector V, and this will be the projection. Again, the conditions are that V is orthogonal to anything in the subspace, and the projection is in the subspace, and in that case it is called the orthogonal projection. So that is what we will be computing. This condition is that the vector V perpendicular with anything in U is 0. So the first observation is such decomposition is unique. So these two summands are uniquely determined, as is sort of obvious from the picture, because if we're looking at the midday shadow, it is unique. Let's prove it mathematically. Let's imagine two decompositions into something which are called W and U, and W prime and U prime. So these U's will be two possible projections. They're in the subspace. U and W's will be both orthogonal to what we project onto. So then we should be able to prove that these two these two pairs of vectors are actually the same. Let's look at their difference. So we have this equation between them. The sum of W and U is the same as the sum of primed versions, and we can rewrite this equation in a different form. The difference of W and W prime is the same as the difference between U prime and U. So now this time this side is totally in U, because separately U and U prime are in the subspace U, and then by properties of subspace this will also be in U. But we also know that W and W prime are orthogonal to anything in U. So when we will be computing the scalar product of W minus W prime with itself, we can rewrite it as the scalar product of W minus W prime with this vector which is in U. Anything in U is orthogonal to W and orthogonal to W prime. So rewriting our scalar product like that, we will see two scalar products of W with something in U, and then W prime with something in U. they both should give us 0. So this scalar product of a vector with itself is 0, and that only can happen with the vector is 0. And that is also the same as to say that the vectors w and w prime are the same. But if they are the same, then so are u and u prime. And we proved what we wanted. We proved that if we have two possible decompositions like that, these decompositions are just one and the same. That uniqueness is done now. So now let's look at practical ways of computing this orthogonal projection. Applications of this orthogonal projection will come later and will be quite numerous. Let's imagine first that we have a special presentation for our subspace. It is a subspace spanned by a collection of vectors. That is not very special, but we will assume first that this collection of vectors is special with respect to the scalar product, something which is called orthonormal basis. What it means is that scalar products of two vectors from this basis are either 0 if vectors are different, or 1 if vectors are the same. In other way, different vectors are orthogonal to each other, and the same vector has unit length or unit norm. So that is called orthonormal basis, and that is the easiest situation to work with. The answer for the orthogonal projection on such subspace will be one easy formula. As a vector in a subspace, it should be writable as a combination of basic vectors. All we need to know are what are the coordinates, and the coordinates are just scalar products of the vector and the basic vectors. Coordinates are computed by scalar products with corresponding basic vectors in an orthonormal basis. So that is the formula, which is very convenient for computation. The input is rather restrictive, but yeah, let's first prove this formula. What do we know about this orthogonal projection? Is that the vector without this orthogonal projection should be orthogonal to anything in the subspace. So we know that the vector without the projection should be perpendicular as one vector to anything in U. Anything in U is a linear combination of basic vectors, so let's just look at one of them and make it arbitrary and see that for arbitrary basic vector we have 0 here. So that's what we're after. Let's expand. The formula which we have, let's write it in a compact way as a compact sum. V scalar product with some basic vector, changing the running index in the sum to something different to the index of the vector I'm computing the scalar product with. And now we could use linearity. So that's why linearity is really helpful. Now I could use linearity in the first argument and rewrite this scalar product as many scalar products, and distributing through the sum and taking this scalars out, I will have a scalar product of arbitrary basic vector with this concrete one, number I. And by condition, by the orthonormality, this is 0 most of the time, and it is 1 when j is equal to I. And so we will see the difference of two identical terms. Because when j is equal to I, it is 1, and so we have total cancellation, proving what we want, that the difference between what we want to be the projection and the vector is always orthogonal, and by uniqueness that must be it. So that is a very easy formula, well, relatively easy formula, but in the restrictive case of having an orthonormal basis. A more practical assumption would be that just to have a basis which is orthogonal. This is something less than orthonormal, but it still assumes that different vectors in the basis are perpendicular, but it doesn't require vectors to have unit length. If they don't have unit length, then we can make them to have unit length by this adjustment, by rescaling them with their norms. So if we have an orthogonal basis, we can make it orthonormal by this procedure. So let's see what it gives us in terms of the projection formula. I will write the answer straight away, and then I will argue for its validity. The adjustments will be in these denominators, which will be squared norms, or just scalar products of our coordinate vectors with themselves. So now, proving this more general version of the projection formula, we could reduce this case to the previous case by doing the scaling of coordinate vectors. So we are projecting again onto U of some vector v, and in terms of this orthonormal, we will have just the sum of scalar products used as coordinates for this orthonormal basis. And then just remembering what these orthonormal basis vectors are, we have to see two copies of the norm in the denominator of the coefficient. And the square of the norm is nothing but a scalar product of that coordinate vector. So we have it verified, we have it reduced to the previous case which we proved before. That will be applied in the next video, when we will talk about orthogonalization process, finding this orthogonal basis. See you then.